Unit 6, pages 117 to 126, Modern Quantum Theory. Modern quantum theory used a new approach to describe the physics of atoms. Electrons are described using a mathematical function psi that treats the electron as a wave. A wave equation, the Schrödinger equation, is used to solve for the physical properties of the electron. No assumptions are made like electrons move in orbits. The modern view of the atom. It's impossible to know the motion of electrons in atoms. Each electron is described by a mathematical wave function psi. The wave function has no physical significance. However, psi squared is the probability of finding the electron in a certain region of space. The energies are quantized. 4 quantum numbers, n, l, m sub l, m sub s, describe each electron. Electron orbitals. We cannot know precisely how the electron moves. Instead, we think of the regions in space where the probability for finding the electron is high. An orbital is a map in space of the high probability regions for finding an electron. Orbitals, as an analogy, suppose there's a hive of yellow bees that only works at night. We cannot watch the bees in action or know how an individual bee moves, but as they work, they leave behind a trace of yellow color. In the morning, when the sun comes up, we can get a picture of where they have been. There are yellow dots everywhere, but some regions where they have been very active have thick yellow color. That picture is a map of probability, very much like an orbital. Now, in the case of electrons, their path is completely unknown to us. It's important to realize that the physics of electrons and atoms does not allow us to know their movement. No clever device will ever make this possible. So what we can know is the probabilities of finding an electron in an orbital or specific location. The movement of the electron, however, cannot be known. Here's a summary of determining quantum numbers. N is the first quantum number, which can equal 1, 2, 3, up to 7. It is called the principal quantum number, or also representing the principal energy level. It's the orbital size, the energy of the electron, and its shell number. L is going to be 0, 1, up to n minus 1, and is known as the azimuthal or angular quantum number. It's going to represent the shape of the orbital, such as S, P, D, or F. M sub L is going to be equal to the negative L up to the positive L, and you're going to have that for each L value. This is called the magnetic quantum number. It tells you the orientation of the orbital in space. And then each ML value has 2 possible MS values, a plus 1/2 or a minus 1/2, which is the spin quantum number, whether or not the electron is spinning clockwise or counterclockwise. Orbital shapes. The angular momentum quantum number L determines the shape of the orbital. The angular momentum quantum number characterizes the angular momentum of the orbital. So if you were to have L equal to 0, then that's representing an s orbital or a spherical shaped orbit. If you have L equal 1, that's called a p orbital, or it's like a figure 8 or a dumbbell shaped orbit. L equal 2 is a d orbital, which can look like this or like this. And then L equal 3 is an f orbital, which you're not required to know the shape of it necessarily. So when you see an orbital notation like 3p, the 3 represents the n value, n equal 3, while the p is going to be L is equal to 1. Here for 2s, n is equal to 2, while s tells us that the L is equal to 0. You must know everything in this figure above. Orbital orientation in space. The ML quantum number determines the orientation of the orbital in space. There is no simple connection between ML and the Cartesian XYZ axis. The magnetic quantum number M sub L describes the projection of the angular momentum on an axis. So for example, when you have a p orbital, when L is equal to 1, you can have ML values of -1, 0, or +1. Or say that the p orbital is moving on the y-axis or the x-axis or on the z-axis, to be simplistic. Degeneracy. The 3p orbitals have the same energy. They are energy degenerate. However, in the presence of a magnetic field, the energies split because each orientation interacts differently with the magnetic field. So here you have no magnetic field, so they have totally even or equal energy. And then when you add a magnetic field, then they're going to end up with different energies, and they're going to move separately a bit. Energy levels and shells. For a hydrogen atom, the energies of the levels depend on the principal quantum number n only. This picture shows the relationship between the energy levels and quantum numbers in the n equal 1, 2, 3 shells of the hydrogen atom. As n gets larger, the size of the orbital increases. As n gets larger, the orbital energy increases, and as n gets larger, there are more possible suborbitals, shapes, and orientations described by L and M sub L. The idea of a shell, same n, is only for convenience of grouping orbitals together. It does not mean that there is one eggshell inside another shell. All of these orbitals are intermixed in space. A subshell means the same n but a different L value. So n is going to be called a shell, and then L values are called subshells. The n equal 3 shell contains the 3s, 3p, and 3d subshells. So here, if n is equal to 3, you can have the 3d subshell, the 3p subshell, and the 3s subshell. In n equal 2 shell, there's a 2p subshell and a 2s subshell, and in the n equal 1 shell, there is only a 1s subshell. Lowest and highest energy levels. The picture below is an analogy for the energy levels of the hydrogen atom. So here, whenever you have the electrons closest to the nucleus, they have the most negative energy, energy less than 0. They have the lowest amount of energy. And as you work your way up, away from the nucleus of the atom, you work your way to having energy 0, which is the highest energy. It's infinitely away from the nucleus. So the most negative energy is possessed by the 1s orbital, and then it becomes even less negative energy as you move up towards the highest energy, which is energy equal to 0. Imagine one man near the top of a series of steps and another near the bottom. We choose to define the top step with an energy of 0, so the bottom step will have a negative value of energy. To climb out of the hole, they must each do work against the force of gravity. The man near the top has less work to do to climb out of the hole because he is standing closer to the top on a higher energy step. The man at the bottom has work to do as he is standing on the lower energy step. Relationships between quantum numbers. Looking at the figure above, you can see certain relationships between quantum numbers. The second shell is described by n equal 2. This shell only has an s and p orbital. Apparently, when n is equal to 2, L can equal 0 and 1, but L cannot equal 2. Notice also when L equal 1, the type of orbital is a p orbital. When L is equal to 1, ML can be values of -1, 0, and +1, but ML cannot equal -2 and +2. The following table summarizes these relationships. N can be any value from 1 up to 7. L is going to be 0 ranging up to 1 less than whatever your n value is. M sub L is going to be for each L value ranging from -L to +L, and then MS is going to be for each ML value can be +1/2 or -1/2. You must know these quantum numbers depend on each other. A certain electron has a quantum number ML equal to -2. What are the possible values for N, L, and MS? So here we can write out our little chart, and you have an ML value that could be -2, which means that it can range from -2 up to +2. Each ML value can have a plus or minus 1/2. And so if you have an ML value of -2, that means you could have an L value equal to 2. And that means that your N would have to be equal to 3, because L can range from 0 up to 1 less than N. So N could be 3, L can be 2, giving you, and then ML can be 2, and you can have a +1/2 or a -1/2. And this is the minimum that L has to be, so we could continue forward, and it could be any number. L can be any number greater than 2, 2, 3, 4, etc., which means that N, as long as it's at least 3, it can be 3 or anything greater than that. Exercise 6.39. Which of these sets of quantum numbers is not allowed? So N equal 2, L has to be any number less than 2, which that is. And then if your L is 0, your ML can only range from -0 to +0, which it is. And then your MS must be at least +1/2 or -1/2. So letter A is a valid set of quantum numbers. N cannot equal 0, so this is not a valid set. N equal to 2 means that L has to equal anything less than 2, which it does. If L is equal to 1, then your ML ranges from -1 to +1, which means this is not allowed because it's not within that range. So this is an invalid set of quantum numbers. If N is 2, then L is equal to -1. No, that's not true. It's going to be 0 up to 1 less than n, so that does not include negative numbers. So letter A is the only valid set. Electron spin. The property of electron spin is a relativistic effect that requires Einstein's theory of relativity to explain. There is no classical analogy. Nevertheless, we imagine the electron spinning like a top, creating an angular momentum accompanied by a small magnetic field. The spin is quantized with two possible values. Normally, we refer to the two possibilities as spin up and spin down. Electrons in a magnetic field can be separated into these two types. So generally up arrows will be an ms of +1/2 and down arrows be an ms of -1/2. Here's your note card for this section. Quantum numbers are usually represented in parentheses in this order: the n value, L value, ml value, and ms value. N is going to represent the distance from the nucleus, which is the principal energy level. Ranges from 0 up into 7. It corresponds to each row on the periodic table. L is going to represent the shape of the orbit and is sometimes referred to as a sublevel. It's going to range from 0 up till 1 less than the n value. If you have an L equals 0, you have an S-shaped orbit. L equal 1 is P, L equal 2 D, L equal 3 is F. Each L value has an ML value, which is going to represent the orientation, and that's going to be referred to often as the orbitals. It can range from -L to +L for each L value. It's represented by blanks in an electron configuration. So if you have an L equals 0, then you can only have an ML of 0, which means you only have one orientation. So that would be the S orbital has only one orientation. The p orbit can range from -1 to +1, which means it can have 3 orientations, and so we represent it with 3 blanks. You arbitrarily label them 1, 0 to -1, the range of -L to +L. And then the ML value for L equal 2 is going to range from -2 to +2, which is going to give us a total of 5 orientations, which is what the D orbital is capable of harboring. And then each ML value has 2 possible MS values, a +1/2 or a -1/2, represented by up arrows and down arrows. So if we look up here at this diagram, then we can see that when you have a 1s sublevel, the n value is equal to 1, the s tells you that L is equal to 0, and then the ML value is represented by there only being one blank, which is going to be labeled 0, because that's -L to +L is just 0. And then the 2 up arrows and down arrows are going to be +1/2, -1/2 as my spin value. If I look at the 2p3 that I have drawn here, n is equal to 2 because of that 2 right there. The p tells me L is equal to 1. L equal to 1 can have a range of -1 up to +1, which is 3 orientations. That's why we have 3 blanks. And then because each blank only has an up arrow, they each have an MS of +1/2.